So hello, my name is Rafael Noga, and I will present a prototype application of non-linear moving horizon state estimation and control to the superfluid helium cryogenic circuit at the Large Hadron Collider. So we will start with an introduction of this challenging control problem of temperature stabilization at 1.9 Kelvin plus minus 0.1 Kelvin over the 27 kilometers length of the machine. And then we'll have a look on the advanced controller and its key components, which are the first principles model of the superfluid helium cryogenic circuit, Luenberger hybrid Luenberger observer moving horizon state estimator, and the non-linear model predictive controller. Then we will discuss the experimental results taken from the experiments taken at the LHC, and we will finish with conclusions and outlook. So the Large Hadron Collider is the world's largest and most powerful particle accelerator that has enabled the discovery of the Higgs boson and the Higgs field in 2012. So this trace corresponds to the 27 kilometers of the circumference of the LHC, but you don't see the machine in the photo because it's placed 100 meters underground in a tunnel, and this is the LHC. So what you see here actually are thousands of superconducting magnets. Those are the superconducting coils here, cooled with superfluid helium. In order to keep the temperature below 3.3 Kelvin, the superfluid helium itself is available below 2.2 Kelvin. And so the LHC is subdivided into standard cells. Each of them is 107 meters long, and in those cells we have in each of those cells we have 8 superconducting magnets, and then we have helium throttled at a control valve, fed to a bayonet heat exchanger, 100-meter long bayonet heat exchanger, where it flows, boils, and takes away the heat. So finally, the magnets are placed submerged in a static bath of superfluid helium kept at 1.9.1 Kelvin, and then this helium bath provides the heat connection between the coils and the heat exchanger. So please note that only one extremity of the heat exchanger is wetted, so that the heat must flow through the magnets to get to the wet extremity. And two of those standard cells, interconnected hydraulically, correspond to a 240-meter long subsector of the LHC. So this is the actual control problem that we're gonna tackle, and so we have two valves used to control the flow in 2 bayonet heat exchangers, and we have altogether 16 superconducting magnets. So let's have a look on the operational data from the LHC taken at operation with the half of the nominal power, because until now the LHC has been operated at half of the nominal. And what we see here are the perturbations, the strong perturbations, which are related to the current flowing through in those coils. And then what we see here, the black lines, are the temperatures. So basically they are distributed temperatures over 214 meters. There are 16 of them. There's at each of the magnet. And what's interesting to notice is that the temperature distribution over 200 meters is very homogeneous. So basically the difference here corresponds to some maybe to 100 part of a Celsius degree here. So this is really a small temperature, but it's very small temperature difference. So this is only possible actually due to the very high thermal conductivity of helium-2, and this thermal conductivity is also the reason behind the very strong thermal couplings between the standard cells in the subsector. So what you see here is that one of the control valves is almost closed and the other takes over the cooling because of this very strong thermal coupling. Another problem is that the dynamics of the circuit changes very drastically with the changing with increasing temperature gradients, because the thermal conductivity of helium-2 is a strongly nonlinear function of those temperature gradients. And this is what we see here on the left side. We see the standby conditions. So we see the heat load corresponding to the standby conditions. There are some 40 watts of heat load introduced to the system, and there are some introduced to the system, and we see almost no temperature gradients that appear only when we increase the cooling power. And then we have another case where 40 watts of extra power is introduced equally along the 240 meters, and then what we see is much higher temperature readings and very different temperature dynamics. So basically we observe strong inverse response and the changing dead times of response. So it's a totally different control problem it becomes a totally different control problem after the conditions have changed. The problem is still more complicated than that, because we still have operational constraints, and the constraints are related to the minimal temperature and inner magnet temperature that's allowed, because here actually we have the saturation temperature, the temperature of the heat exchanger, and the temperature of magnets cannot be lower than the temperature of the heat exchanger. And if we approach it, actually helium starts to accumulate in heat exchanger, and it causes in the overflows and it causes helium accumulation in the phase separator, and the phase separator cannot overflow. This is the very serious constraint on the operation of the circuit. And on the other side, we have a constraint on the maximal temperature here, which is at 2.1, because here we are approaching actually the limit for the existence of the superfluid helium. I mean, the superfluidity is low at 2.16, so the 2.1 gives us a safe margin. So basically the LHC cannot run if the temperatures decreases or increases above this temperature level. Another important constraint is related to the mass flow rate flowing through those valves, because the sum of the mass flow rates in the 27 valves distributed along the 3.3 kilometer sector of the LHC cannot change too fast, and the limit of this mass flow rate and the mass flow rate absolute values are also limited. So this is a very complicated and challenging control problem, and we will try to solve it to improve the control of this problem using an NMPC controller. So in the NMPC directly addresses the model nonlinear dynamics, complex interactions between process variables and operational constraints, but the total computational complexity of the model simulation numerical solvers used in the optimizations must allow for its real-time feasibility. And then the model of the process is the key component of this model-based technique, and we see that we need to model very complex behavior, because we have many different heat transfers occurring in the system between different components of the system, and we have different mass transfers in the system, including some three-phase flows and two-phase flows of helium. So it is a complex system. It looks complex, and it is a complex system, and we still need a model that enables that we can actually simulate at a very low computational cost. And this is what we achieved by clearly defining the model validity range, so that we could use a description that covers only that range and use a lot of approximations with simplified expressions. And we also managed to do this by strictly controlling and limited the fastest model dynamics. So we used approximations to approximate the original dynamics to cut the fastest dynamics, or just to neglect the modeling of those fastest dynamics. And then also by choosing the spatial discretization grid with lowest acceptable number of steps corresponding to acceptable modeling errors. So this first principle model has been finally discretized with 21 steps corresponding to some 6.5 meter long intervals, and then the model has 262 dynamic variables, 18 input variables, 20 output variables, and 1 parameter. And out of those 18 input variables, those are the two mass flow rates at the control valves that we can influence, and also the heating power of the electric heaters that we installed in the machine. The others are perturbations with strong influence on the system behavior. So the big problem is that the majority of the states and inputs is not measured, which means that they need to be estimated first, and this we can do with the moving horizon state estimator. So the moving horizon state estimator it's an estimation technique when you again use nonlinear model and optimization in order to solve to estimate this inputs and parameters. But the optimization problem in case of this discretized PDE system is ill posed. But so we have a problem. We cannot use directly. But luckily, not all of those variables actually that we have to optimize, that we have to estimate, must be explicitly optimized. So actually we will identify first some variables with direct impact on the measured variables, and then we can use simple Luenberger observer in order to get those variables, and then we will use the optimization only for those variables with highly complex influence on the system behavior. And finally, the other variables, they will converge. Well, the other they will converge to the actual values, given that the other variable groups are estimated correctly. So we obtain this type of structure. So the inner part here, the model in the loop, is simulated over the past estimation horizon, and this is the Luenberger observer. The loop is the Luenberger observer, okay, and this is where we estimate the heat load into the magnets, and then the two other parameters, and then there are just two other parameters. So the contour mass flow rate, the exact value of the contour mass flow rate at the valves, and the saturation temperature that we are actually optimizing using the moving horizon state estimation approach. And this formulation is one corresponding to well-posed optimization problem, and it allows for real-time feasibility of the optimization. So now we can use the non-linear predictive control. Having those states, we can use the non-linear predictive controller, and then what we do is we will optimize the true trajectories of manipulated variables over a future time horizon, and which are we first parameterize using basis function sigma. So in this way, we actually got just six variables that we need to optimize, and then this optimization problem isn't solved at each 20 seconds. What's interesting here is that actually in order to solve the nonlinear optimization, nonlinear quality constraints very fast, we have transformed it into a nonlinear programming problem with box constraint by including all non-box constraint into the cost function using an asymmetric quadratic cost, like this. So basically in this cost function that we are minimizing here, we have in this cost functional that we are minimizing here, we have then the cost corresponding to the initial control objective, and those costs corresponding to the constraints, the non-box constraints. So this problem, actually, this optimization problem with box constraints, we can tackle it using a single step quasi-Newton optimization approach, where we are it's an iterative approach, but here we have just one step where we are calculating the optimal value of our optimized values using the previous ones and the search direction multiplied by a factor corresponding to the line search. So the line search, these values we actually take from a fixed set of the components, so we just simulate for all of those, and then we take the one that corresponds to the minimum. And then what we need to do by while calculating the search direction, actually, we need to take into account the case where the diagonal, it's a quasi-Newton, so we only use the diagonal components of the Jacobian, of the Hessian, of the Jacobian, of this functional, but but some of those can be negative. Okay, in order to cope with this, we then use this condition actually, and then if they are negative, then this approach is actually transformed into steepest gradient. So we calculate the step for the variable using the steepest gradient, steepest descent approach. So this is what we have implemented actually at the LHC. So we have implemented this controller, this advanced controller, into the SCADA system of the LHC, which allowed us to use this C code that we use in the simulations directly via drivers. And then we were also using SCADA, we are also able to access all the available process measurements and also send values of manipulated variables, of those optimized variables, to the PLCs that are in the manual mode. So the length of the horizons for the state estimation that we used was 30 minutes, and that for the predictive control of 120 minutes. And as we mentioned, the control update was of 20 seconds. So 20 seconds each, 20 seconds we repeated the optimization. And the results, the experimental results are very interesting, because still again we have two different cases at two different heat loads that we see that where the dynamics change so strongly. So the first one to the left corresponds to the nominal operation of the LHC that we still have not experienced because the LHC was running under half of the nominal power, but still we simulated here, and we see there is some temperature gradient bigger than what we've seen currently until now with the half of nominal power. And then in the second case actually we see much more of this gradient. Okay, this is because here we increased the heat load. Well, we introduced it using heaters, and then the basic value here is at 60 watts, which corresponds to 1.5 the nominal standby value. Okay, so what we see here actually that the lower temperature is not really responding to the controls anymore. And the reason for this is that this is saturated. So this temperature now corresponds to the temperature of the heat exchanger. So it's just strongly saturated. And so we see that even though now we have very different conditions and very different temperature distribution, and also the strong saturation effects, we have almost identical closed loop dynamics. And also we are respecting constraints on the maximal rate of change of the helium flowing through the valves. Okay, and we do it at very low computing cost of optimization, because we need something around 7 seconds in order to update the controller for the NMPC, and less than a second to update the estimation in this hybrid MHSE and Luenberger observer estimator. So the temperature stabilization. So what we've seen is that the temperature stabilization of the long bath of superfluid helium is a challenging control problem, and application of non-linear model predictive control and moving horizon state estimation with online optimization is possible to this problem when we use a model, first principles model optimized for low computing cost, and a hybrid linear Luenberger observer moving horizon state estimation approach. And when we formulate the optimization problem as one with box constraints and we use a simple single quasi-step Newton solver to solve it. And then the performance of this approach, of this advanced controller as tested at the LHC, is far better than that of the PI controllers currently used, and would allow to face the control problems that may appear while operating the LHC at full power. So there are some possible future developments actually that we could do. So since the model is so good that it enables such a very short time for the optimization, so we can also think about using the electric heaters as the manipulated variables. Okay, and then we have a problem with 18 optimized variables, so it's still we still manage to optimize it in the time lower than those 20 seconds available for the update. And then another possibility is to try to operate closer to the saturation temperature. The saturation effects, very strongly nonlinear effects, are much stronger, and but the difference in temperature, the temperature is much more homogeneous because it's limited by the lowest temperature. And the other possibility is still very interesting possibility is to extend the advanced controller over 3.3 km log sector to better cope with these constraints on the maximal and minimal mass flow rates and the rates of change of the helium flowing through the 27 valves. So thank you very much for your attention. And this is my small message, but basically I'm looking for a new challenging project, so feel free to contact me if you know any. Well, this is my email address, thank you. And voila, do you have any questions? Please ask on Facebook. Bye.